Physics time. Da-da-da. Okay, let's hey, close your eyes real fast, real fast. I left the answers to the quiz on. No, don't look, don't look, don't look. No cheating, cheater pantses. It's not for points or anything. You didn't look, did you? Okay, you can open your eyes now. Liar, I lied. It's a fake news. Anyway, A through E in the Jujel form. Let's see what you know. Don't work together on these. You got to do them individually first. Then you can talk to your neighbor once you're both done. But I want to see what each individually knows. Where's that go? Yeah, 3 minutes. Hey, where's an A under? No, it's in the Google form. Spot A. Question A is asking the defining equation for electric field, not in capacitor, the general true always definitional equation. We'll get there. It's Zoom time. All righty, time's up. No, really, now time's up. Okay. I want to see what you guys know. You got stored your brains. Not what takes 5 minutes to retrieve. You know, or you don't. Here, on these different. Okay, so let's go over these. Hey, by the way, you know never to change your answer in Google form, right? Unless I say we're going back and iterating. I want a record of where people are struggling and where people are getting stuff so they can see what I need to bang on harder and get more time to, yeah? So don't change your answers unless we're specifically saying I'm Socratically logically you through the answers so you can learn something. Defining equation for electric field, that is always true, definitionally true. You know the triple equal sign? I use triple equals, the 3 bars to indicate always universally definitionally true. You can always rely on this. Force per test charge. Newtons per coulomb. Oh my God, electric field. Hey, force is the newtons, Q is coulombs. Newtons divided by coulombs. If I double the distance, then the formula force equals KQQ over D squared, or I think I've been writing R more often. If R doubles, 1 over R squared quarters. Note there is a difference between 4 and 1/4. Which do I put on top? Old or new? When I say if I change, I'm saying I have a new configuration. If I double the distance, R becomes twice as great. Which goes on top? Which goes on bottom? New on top, old on bottom, always. Okay, so correct answer is 1/4, not 4, 1/4. Equation for E inside a capacitor, electric field, not triple equals Q over A epsilon naught. You guys remember what these terms mean? Charge on one of the plates, area of one of the plates, constant. Remember that? It was at the end of last lecture. And it's important. We're going to be using him left, right, and center today. And equation for voltage near a point charge, a Q on R. What's the voltage near a positive charge? If Q is positive. This should not be a challenge. What is the voltage near a point charge if the charge is positive? Q is a positive number. Is distance ever negative? What can you tell me about voltage near a positive charge? Positive. Are you sure? You should be positive. As R gets smaller, as the downstairs of the fraction gets smaller, what happens to V? Bigger, right? The closer you are to pluses, positive charges, the bigger your voltage gets. At least if it's a point charge. What happens if Q is negative? As I get closer to a negative charge, what happens? Tell me about the sign if Q is negative. Negative voltage, less than 0 volts. 0 volts is infinitely far away from the point charge. What happens is R gets small. I get negative and negative and negative. One of the takeaways that the 3 o'clock struggled with is where you find positive voltages near positive charges. There's point charges, where you find negative voltages near negative point charges. Remember that. Okay, now let's take a quick poll of the class. See, you're golden. Thank you. Okay, that's a lot of correct answers for A. Good. For B, electric field, got a lot of correct answers. Quarters. Oh my God. The 3 o'clock class had so many 4s. But Q over A epsilon, not KQ over epsilon, Q over A epsilon, Q over A epsilon. Not as many, but it was the last slide. I get it. Okay, so decent on D. KQ on F, what you smoking? KQ on R. KQ on R squared. KQ on R, KQ on R, KQ on R. IR, no. IR applies for resistors. Not a point charge. KQ on R, 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 KQ on R. I also forgot KQ on R, KQ on R, KQ on R. Don't recall KQ on R. Okay. Hey, this paying attention to the 4:30 is harder. I get it. It's late. We're tired. You guys just kicked the butts of the 3 o'clocks. Good job. On average. Okay. So we got a good foundation here. We're definitely ready to push forward into this. Let's actually see the slide. Here we go. Whoa, that's a lot of information. Well, actually, a lot of this is stuff you just showed you already know. First line, capacitors, the topic for today. Well, most of the topic. The symbols that you will see, I will always draw the first symbol with a curved bottom. I think it's prettier. You will also see in the textbook on the homework system, I'm sorry, 2 straight parallel lines. Please note, battery also has straight lines. The difference between a battery symbol and a capacitor symbol in the textbook and the homework system is that a battery always has a longer and a shorter line. Longer line is the positive, shorter line is the negative. Yeah, remember that? Okay, so you can rely on that. So they're 2 equal length parallel lines. That's a capacitor. Or if one of them is curved, that's A capacitor has a billion uses, but one of them, what we could say in general is a capacitor, can be used as a storage tank for charge, as a balloon. We fill up with charge, we blow up the balloon, and the more charge we put in it, the harder it is to inflate more. It's got some charge in it, and we can use that charge to do stuff. I want to bang on this for a second. I want to tell you what the capacitor is not. Capacitor is not a battery. A battery is not a balloon filled with charges. A battery is a pump that pushes charges from one side of the battery to the other. Remember this? Battery takes chemical energy and delivers it to the charges inside the wire on the negative side and pumps them up. I want you to up. Boosts their energy and pushes them out with constant voltage on the other side. As we will discover in 15 minutes, I think, the voltage of a capacitor is very, very not constant. Capacitor would be a crappy battery. Battery, steady voltage. Capacitor, very not steady voltage, as we will find, as it discharges. Okay, the electric field in particular, a parallel plate capacitor, this is not a universal. But for the only kind of capacitor that we're going to deal with is given by the equation Q over A epsilon. I already said Q is the charge on a plate, A is the area of either plate, epsilon's a constant, there's his value. Deja vu, yes, no, maybe so, is good? Ah, comrades. Okay. Note here, the unit for capacitance is the farad, F. And do you know what a pico is? 10 to the minus 12. Picofarads are totally common uses, totally common practical values of everyday capacitance. Usually tens or hundreds of picofarads. But you must know pico is 10 to the minus 12 if you intend to solve the problem correctly. Right? Standard unit is the farad, so if you see picos, multiply by 10 to the minus 12. Does that sound good? Also, how do you make a capacitor? Well, there are lots of ways, but the simple kind that we're going to describe has two conductors, two sheets of metal, separated by an insulator, separated by vacuum, air, whatever. And you can connect it to a battery, and the battery will pump positive charges onto one plate, negative charges will be on the other plate. And this is a storage tank for charges. If I take it instead of from the battery to some other circuit, these pluses can flow off, these minuses can flow off, delivering charge to the circuit. Parallel set of plates. Hey, little parenthetical note here. I drew 9 pluses here and 7 minuses there. That's just because it's a perspective drawing, perspective sketch. There are 2 minuses hidden under there. The total charge on any capacitor is always, always, always 0. That's why I said charge on a plate. You're gonna have a plus plate, you're gonna have a minus plate. And the total, you've got 5 coulombs on this plate, you've got negative 5 coulombs on the other plate. Never plug in the total charge because total Q is always 0. It's the charge on whatever plate we're considering whatever plate we're not considering the reference. Whatever plate is not reference. Okay, so and I'm just going to remind you again for this because it is a way to goof. A is the area of either plate, not both at the same time. Okay, now which way does electric field point? From plus to minus or minus to plus? No. Naughty. Da. Okay. Oh, unless that's Jameson, in which case you got good. I mean, fine. Positive to negative. Electric field points from positive to negative. Why does it point from positive to negative? Electric field is force on a test charge. Force divided by test charge. If I've got a positive test charge, does a positive charge want to go from positive to negative or negative to positive? Positive charge is attracted to the opposite, repelled from the light, yeah? Opposites attract. Positive charge would want to go to the negative plate. Electric field points towards the negative plate. Does that make sense? Why? Don't memorize facts. Facts are fragile. Memories and facts are fragile. Memory is reasoning. Electric field always points from positive charges towards negative charges. And this is why. Yes. Electric field always points from positive charges to negative charges. Always, 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 always. Electric field leads positive charges and aims towards negative. And why? Why does it? Because like charges repel. Positive charges want to get away from other positive charges. The force is in the repulsive direction. Positive charges are attracted to negative charges. They want to go towards negative charges. Don't just memorize. Don't just memorize fact. Reason. Yeah.
Question said that like protons are moved. It's like a concept.
Yes, field is not charged. The charges make the field, but the field is not the motion of the charges. He's absolutely right. If I actually attach a battery to this, I describe this as saying positive charges leave the positive side of the battery and deposit on the plate. That's actually a lie. The direction of motion of stuff is negative charges are slurped off. But our model for electricity is, as it turns out, there is no experiment you could do except for one tiny thing that I might mention in passing. Everything we do this entire semester, you can imagine the charge is carried by little pluses. And it doesn't screw up. You can think of the pluses as electron absences, right? If an absence of a negative goes this way, a positiveness goes that way. If negative goes this way, its absence goes that way. Okay, so question. That was a good question. Both of you good questions. You can have donuts if you want. Okay. Which side of the plate has positive voltage? Which side of the plate, where are we going to find the plus voltage? You find the positive voltage, you have the positive charges. I put plus charges up here. This is where the positive voltage is going to be. Does voltage increase or decrease in the direction of the electric field? If I walk along the direction of a field vector, voltage goes down. Write that down. Voltage decreases in the direction of the electric field. If I attach the minus terminal here and the plus terminal here of the battery, yeah. This plate would get pluses, this plate would get minuses. So I rewrite it, some everything. There are some capacitors, polarized capacitors, electrolytic capacitors that have a material inside that can only be charged one way. If you put it backwards, they pop, they blow. So the battery looks like this force that rearrange. So we're going to talk a lot about the rearrangement process. Keep asking about that. I'm going to try to explain that. It doesn't make sense. Okay. Again, I want to bang on this point. Have a second. I want to bang on this point for a second. Electric field points towards negative charges. Yeah, making sense? Opposites attract. The charge, a free test charge with a field pushed down. But voltage decreases in that direction. Why? Voltage is positive near positive charges and negative near negative charges. Here's an analogy. Which direction does gravitational force point? Right? Gravitational force is related to electric field. It could be, you make an analogy there. Which direction does gravitational potential energy increase? mgh goes up as you go up, yeah? So if I go in the direction of the force, have I increased or decreased my potential energy? Decrease. I decrease voltage by going in the direction of the field. I decrease my gravitational potential energy by going in the direction of its associated force. Does that help? I really want you to understand that. Questions? Two questions, actually.
Does that mean it's less energy on the negative side?
That means a positive charge loses energy. You could get kinetic energy by allowing it to go from the plus to the minus. Yes.
If I were to take a voltmeter, put one on one side and one on the other, there will be a drop in voltage.
The voltmeter would read a negative number if I measure this terminal relative to that terminal. If you reference commonly here, measure the voltage here, it will be a negative number.
Switches.
Question?
Has the resistors have a change in voltage at a certain field?
There is an electric field inside a resistor. You don't want to think about that. Trust me, it's hard. Every time voltage changes, there is an electric field associated with that. Trust me, you don't want to go there. Yeah, I know. Good questions. I should have brought one of those. Okay, so again, one more time. I want to bang on this. Electric field points in some direction. Voltage always decreases in the direction of the electric field. There is a formula which connects displacement along an electric field and the voltage change along that. Bang. I asked this as a Google form question. Screw it. The change in voltage as I walk along an electric field line in the direction of the field vector is that field vector's magnitude times the distance I move. And if I move in the direction, the positive direction, the same direction that E points is my displacement pointing, I lose voltage. If E and delta X are in opposite directions, if I walk upstream, if I walk against the direction of the force on a positive particle, negative gives me a positive change in voltage. It's summarized by saying electric field times distance along that field in the direction of the field. If it changes voltage, and voltage decreases if you go in the direction that E points. It'll be very important, especially for the little bit of extra that we're doing next time. By ED, field times distance amount. Hey, how much does MGH decrease? MG times H change. If I change my height by H meters, how much does MGH decrease? Force times distance.
Depends on like right here, like right here. They can keep going down.
Look, force times distance, the potential energy in this analogy, mg times change in height is change in gravitational potential.
Right? How do we know when? How do we know when it ends? How long delta X is?
When the electric field ends. If you have an infinite electric field over all space, there's no reference point. But every electric field I've ever met has some ending point.
So calculate capacitor electric fields. We don't worry about.
Once you hit the negative plate of the capacitor, the furthest extent of the electric field. Are you guys okay with this? Is good? This is a logical connection between voltage and electric field. This we mentioned last week, but we didn't go into a bunch. In part, we didn't go into a bunch. Mostly, we didn't go into it a bunch because our point charge equations don't have a simple E. E change as X change. How could you multiply two numbers when one is a function of the other? Integral calculus. If you know about calculus, you could do this, but this isn't a calc-based course. Calculus was actually invented to solve problems like this. That's very good. Anyway. But, and this is a big but. The point is, for point charges, you can't just multiply field times distance because field changes with distance. But now we know of a component where electric field is simple. Electric field is just Q over A epsilon. So let's do it, baby. Let's do it. Let's multiply. Let's multiply. Voltage equals charge over A epsilon. In other words, field times distance. Usually, I call this the change in voltage across a capacitor. What? That minus sign that I was just banging on about is gone? Yes, I'm talking about the magnitude of voltage across the capacitor. If you want to think about the physics of electric fields, the minus sign is important. If you want to do practical electronics, usually what we say is the ground terminal is the minus sign. Here's the magnitude of the top sign. Slightly oversimplifying, but this is the way I want you to think about it for now. Again, the minus sign is important if you're connecting the electric field. If you're thinking about the electric field, if you're thinking about the change in voltage inside the capacitor. But if we view the capacitor as a practical electronic device that you're using to do stuff, using it as a component, think about circuits now. Let's use the magnitudes. The reason about the voltage signs happen. Question?
Is the seeming?
Let's see. Oh, yes, the voltage across a capacitor. We have many equations for voltage. We have multiple equations for voltage across different components. What's the voltage across a battery equation? If you say IR, I smack you. Voltage across a battery is constant. You got a 9-volt battery, it's 9 volts. You got a 1.5-volt battery, it's a 1.5-volt battery. Voltage across a battery is constant. What's the voltage equation for a resistor? V equals IR. If you say V equals IR, I know smack you because that's the correct answer. That's right. Voltage across a resistor, that is the one and only correct usage of V equals IR. The voltage change across a resistor. Delta V across a resistor is IR. Hey, what's R? Where's R come from? How do we deduce R? How do we know the R of a given resistor? Remember that formula? Not P, don't say P. Rho. Rho L over A. Resistivity times length divided by cross-sectional area? Yep. What was the big deal that I made? You remember? I went on and on about how rho, L, and A are physical properties of the component, not electrical properties, yeah? Resistance is a property of the resistor. Voltage and current are properties of the electricity that flows through the resistor, right? Let me factor Q times D into a very different form, D times Q. Oh my God, this is the same equation. And meditate upon this, my grasshoppers. D, A, that's closer. D and A, what do those depend on? Geometry. The capacitor. The properties of how you build the sucker. Distance between the plates, area of the plates. Once you build it, it's done. What's this mean? Charge on the plates of the capacitor and electrical property. Capacitor voltage is geometry times some property of the electricity, the charge of it on the capacitor. Resistor voltage, some properties of the resistor times some electrical flow parameter, current. Do you see the parallel here? Voltage equals constant times electricity term. Voltage equals constant times electricity term. The capacitance formula is this, but I'm sorry, we screwed it up 300 years ago. We defined it upside down. Maybe Gauss was standing on his head or something. Faraday was standing on his head. The capacitance for a parallel plate capacitor is the reciprocal of that constant, I'm sorry, A epsilon over D, not D over A epsilon. This is true for a parallel plate capacitor. This is only true for a parallel plate capacitor. This is not a universal physical law. what is the definition of capacitance? Yes, we're only going to deal with parallel plate capacitors in here, but I'd still like you to know what of these things that I tell you is truly universal and what is particular. The true definition of capacitance is here. Capacitance is how much charge you can shove on it per volt developed across it. Definitional equation. Triple equal sign. Always true. Let me motivate this for you. A long time ago, in a galaxy very near, we were doing a lot of experiments. We physicists were doing experiments to discover what electricity is. And we hadn't invented batteries yet. So we used capacitors, Leyden jars, store static electricity to do some experiments. Now, every practical capacitor has an arc voltage. You exceed that voltage and it gets a spark in it. Voltage discharge, the charge discharges and can't do your experiment anymore, but the charge goes to zero. So voltage is sort of what you don't want. Once you get to a certain high enough voltage, that's reaching the maximum. Also, how to get higher voltage is you've got to have your grad student spend more time stuffing their feet on the floor, right? The more effort you have to go into, the more work you have to do on those charges, they boost the voltage. Charge is what you do want. You want to do an experiment with static electricity, multiple experiments perhaps, you want as much charge as possible. Capacitance is a measure of the goodness of the storage unit. How much charge do we get per each volt developed? The higher the amount of charge for each volt developed, the more charge we can store, the longer we can do experiments. Originally, capacitance was called capacity, which is a terrible term. Capacity seems to suggest there's a maximum amount of charge. No, not really. Theoretically, a capacitor could, a perfect capacitor could have infinite charge on it. If it weren't for the arc over, but that's a practical engineering constraint. That's a practical problem, not a fundamental problem. Okay. C is Q over V. You must know this equation. It's very important. And because of this, when we rearrange this to solve for Q divided by V, we end up getting that this coefficient here is actually inverse C. So you could also write this as V equals 1 over C times Q. Write this and meditate, my friends. Write this and meditate upon the nature of it. V equals IR. Voltage across a resistor equals the current through it, some electrical property, times the material constant. Voltage across a capacitor equals Q times 1 over C. This is just like current. This is just like resistance. See the parallel? We're going to use this equation a ton, a bunch, a lot. Write this down. Definitely. V equals 1 over C times Q. We've done a bit. I have motivated and introduced and defined some new quantities. Okay, new equation, C equals Q over V. In particular case, C equals A epsilon of Q. We talked a fair bit about why there's a minus sign in this relationship. I needed this equation to get to the voltage across the capacitor. So we spent a little time on that. And there were some fundamentals here. I want you to take a minute and talk to your neighbor about the puzzle pieces that we done did here before we move on, okay? I'm going to give you 5 minutes, and then I'd like to hear a couple of questions about any part of this, yeah? we are all over this for reals is this time, not lying.
I did not.
This is like. This is.
This.
This is. Only for a parallel.
I think that's a really.
This. This is not. See.
Okay. Keyboard goal. A equals. Yeah. Stop looking. Yes.
Thank you for the question. Alrighty, let's bring it back together for class.
Get this out of
Give
here.
me a question. Give me a question. A lot of information, I get that. Where are you struggling? What makes sense, what's hard? Yeah. Yes, yes, yes. This is important for what we did today. Very important. Yeah. So one way to think about this is an analogy. Voltage is like potential energy, like it feels like force. When we're talking about gravity, mgh is mg times h, right? Why the minus sign? Well, mg points downward. If I go downward times an increase in h, I get negative mgh. I've got to have the minus sign to cancel. So that when I go up, my mgh goes up. If I didn't have this minus sign, going up would decrease my potential. Other questions? Any questions? What's your questions? Any questions on the interwebs, people? People zooming in. If no questions, then we continue. The beatings will continue until morale improves, eh? I would like to talk about what you're going to do in lab next week to prepare you, as I promised on the email. Let's talk about what happens if we actually charge the battery with a capacitor. You can't actually connect the battery directly to a capacitor. If you try, well, the wires or the internal resistance of the battery will act like a resistor. You can do in labs, you can use an external physical resistor, so you don't have to measure those. Also, I mean, if you use a fresh enough battery and small, big enough capacity, you might be able to get something to melt it at fire. I don't know. I don't think the 1.5 volt batteries are gonna do that, but yeah, let's not try. Okay, so we're gonna hook up the circuit. We're gonna take a battery, and we're gonna hook it up to the capacitor, except there's going to be some resistance in the way. What do you know? What have I beaten into your head about the total voltage in series? Has to add up to the total. Yep. So the voltage across the resistor, the IR, and the voltage across the capacitor that you oversee has to add up to the total battery, which is constant. Just for the hell of it, let's say this is a 9-volt battery. When I start out, if I hook up the circuit, the instant I hook it up, what's the charge on the capacitor? 0. If I start out with an uncharged capacitor, start with 0 charge. How much voltage does he have if Q is 0? 0. If Q is 0, capacitor voltage is 0. So if this is a 9-volt battery, and this is a 0-volt capacitor, what can I conclude? Total voltage has to add up. The resistor carries how many volts? None. Okay. Okay. Step 1. This is a multi-step process. Listen up. Pay attention. Multi-step process. You got to think through each step, otherwise it will make no sense at all. Total voltage in series has to add up to the total. Resistor plus capacitor better darn well equal battery voltage. If you start out with a capacitor that hasn't had any time to charge, its Q starts at 0. Yeah. So its voltage starts at 0. If the total voltage of these two adds up to 9, and this starts at 0, then there must be 9 volts across there. The maximum voltage that the resistor is ever going to feel. The full battery voltage. If I apply a lot of voltage to a resistor, what happens to its current? Does current flow? If I apply a big voltage to a resistor, how much current flows? Big or little? Big. V equals I times R. If V goes up, I goes up. If V goes down, I also tapers off, yes? V equals IR, if V goes down, I goes down. What happens as capacitor charge accumulates on its plates? As Q accumulates, what happens to the voltage on the capacitor? Voltage goes up. As this guy charges, he opposes more and more flow going on to him. So there's more and more voltage here. How much voltage is left for the resistor? More or less? Less. There's more voltage here. The total has to add up to the constant battery voltage. There's less and less. What can you say about IR now? What can you say about I now? I is lower. Does I turn around? Does I ever go negative? No. The closer and closer this voltage gets to 9 volts, the slower and the slower the current will put more charge on here. Again, this is complicated. Think this through. The closer this voltage gets to 9, that tapers off to 0. Right? But this voltage never flips around and becomes negative. We never have current flowing in the opposite direction. So this capacitor approaches asymptotically, as we say in mathematics, approaches but does not ever theoretically quite hit. Gets closer and closer to the battery voltage. It's always increasing, but at a smaller and smaller rate. As the resistor has less and less voltage, the current is less and less. Never 0, but accumulating charge at a smaller and smaller rate. Now, turn to your neighbor and tell them this story. It has 5 parts. You gotta think about it. that again? So if you've got a little ripple on your DC signal, you've got a power supply, but the voltage is sometimes the wall is playing a little more, less than what your average wants to be. When you supply more voltage, charge goes onto the capacitor instead of into your circuit. When you apply a little less voltage, then there should be capacitor charge flows off the capacitor to keep your circuit level constant. This example is what happens if I apply just a single switch DC signal to this. So if you've got DC plus alternating current steadily flowing along, the capacitor reaches its equilibrium charge and then just supplies that the input doesn't. This is different. This is switching on DC. Batteries don't change voltage. So the chemicals are all used up. 9-volt battery, that's independent on how much charge it's from. It's just 9 volts. So battery, yeah. Okie dokie, pokey pony, ask me a question. 5-step process. Can you reason through it with each other? David.
So is the voltage negative 9 volts on the other side of the capacitor? Because we go to the.
We usually define the negative terminal of the battery to be 0 volts. Correct. That's the reference.
Okay.
Theoretically, once this is fully charged, you could say this point is 9 volts less than this point. If you define this to be 0 volts, then this would be negative 9.
Okay.
0. Question me, question me. You say. Oh, yes, in the resistor, yeah. As the voltage in the capacitor, if the voltage in the capacitor is smaller, then the voltage in the resistor is bigger. It's actually the opposite direction though. The voltage in the capacitor grows as it charges, leaving less for the resistor. And then as the resistor voltage is smaller, its current is smaller, which means charge goes on slower and slower. Remember, current is the rate at which charge flows. Current is charge divided by time. If current is smaller, then Q increases less quickly. Other questions? Let's graph. Oh, well, here's one graph, voltage versus time, that I was just describing. Capacitor charges. As the capacitor voltage gets bigger and bigger, it gets bigger slower and slower. So it asymptotically approaches, gets closer and closer, but never theoretically reaches the battery voltage. Huh? Is that what you were imagining when I was describing it? Graph, yeah, please.
Like to give a real good example, like when you're filling up a glass of water or something, you pour in a bunch of first, but as you get close to the top of the glass, you have to go slower, have more control of balance. Is that sort of how it works when it's going up?
You can make that analogy. Another way to think about it that I think shows how the capacitor doesn't like to charge is blowing up a balloon. Your first breath blows up the balloon a lot. It's harder and harder to get more and more in as the balloon's pushing back. Right? For any given lung strength you've got, it slows down as the voltage gets higher.
What determines the amount of time it takes to get to the output?
The resistance and the capacitance. The bigger the capacitor, the more storage it has per volt, so it takes longer to develop. The bigger the resistance, the slower the current is thrown. As it happens, there's a parameter called time constant that we may or may not discuss. I don't remember if I put this in the course, which is equal to resistance times capacity. Those units of seconds. Well, I forget. We'll see if we get there next week. Gazunka. Okay, so let's make a graph, not a voltage versus time, but sketch for each other. Sketch on a piece of paper or in your notes, and then turn to your neighbor and argue about it. What would voltage versus charge look like? If I graph voltage on the y-axis and charge on the x-axis, what shape might that have? You can do this. You have all the puzzle pieces. You can assemble. I will remind you that the foundational equation for capacitors is voltage equals 1 over constant times charge. Show me with your hand. Draw voltage on the y-axis, charge on the x-axis. What kind of graph does that make? Huh? So draw a graph relating voltage to charge, and as the y-axis, as the x-axis changes, the y-axis will also change. Yeah. What is voltage when charge is 0? So x equals 0 means y equals 0. What happens if x increases? Does y increase? Does y increase steadily? Yes, y increases steadily, right? Right? Every increase in coulombs, I get a constant multiple times v. What does this look like? Oh, sorry. I can just say that. Did I do it right, by the way? This wasn't my generation. Did I do it right?
It's like a couple generations back.
Was that? Oh my God, that thing's go fast. Okay, so the correct answer is that voltage is directly proportional to charge on the capacitor. Looky at the structure of this formula. Y equals mx plus 0. Y equals constant times x plus 0. What's the constant 1 over c represent on the graph? E is what multiplies x. What multiplies x in the graph y sum x plus b? What does m tell you? That's the slope. Okay. Reflect on this, by the way. It's not c. We defined it upside down. It's inverse capacitance. 1 divided by c is slope. Sorry. Makes it ugly. Next question. Last semester, we talked about slope and we talked about the area under a graph. If we accumulate the y times the x, integrate. Hey, what's the integral of velocity? What's the area under a BT graph? You remember this? Beats in your brains. What's the slope? Displacement. Change in x is the accumulation of v and c. Miles per hour accumulated over hours gives you miles. Okay, so question G, skip over F. Question G, what are the units of this area? Voltage on the y, Q on the x. What is a volt coulomb? You may turn to your neighbor too. It is a single, simple answer. Time's up. Let's see what you put. Joules. Amps. Joules. 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 All right. What was the question? Okay. So again, the question is, what are the units of volts times coulombs? I would like you to remember that volts are defined as joules divided by coulombs, joules per coulomb, energy per charge. If I multiply energy per charge times charge, I get energy. Is good? Make sensey? What's the area of a triangle? Half times all about that base times height, right? How much energy does it take if I charge a capacitor up to some final charge? 1/2 charge times final voltage. Energy is half QV for a capacitor. Energy is half QV for a capacitor. Isn't energy Q times V normally? The units are charge times volts is joules. Why the half? Do you see this? Normally energy is charge times volts, yeah, right? QV is fixed energy. Not along, right. Where's the half come from? Not because there are two plates. Do you all see that this is different from what you might naively expect? We have been dealing with, if you put a charge Q in a basic voltage V, it gains and loses energy QV, right? Okay, meditate upon this, my grasshoppers, and learn something about the nature of energy and voltage. Where does the V come from when we say Q times V? Elsewhere, there are some external charges which are pushing and pulling on that test charge. And when you push or pull on a test charge, you just get to freely multiply Q times V. Where is the voltage coming from in the capacitor? What makes the capacitor have a voltage? The charge on the plates. The charge of the capacitor generates its own voltage. This charge feels the voltage generated by itself. You don't get to use the full charge times the full voltage. The charge accumulates and the voltage increases as the charge accumulates. As I charge a capacitor, voltage is changing. Voltage isn't a constant from some external charge. Voltage is increasing as I charge the capacitor. This is subtle. Please think about this. Please think about this carefully. As the capacitor charges up, the voltage increases. The first bit of charge to go on costs no voltage, costs no energy. The next bit of charge to go on as Q is bigger, V is bigger, and it experiences a bigger charge times voltage for that charge. The more Q increases, the more charge the capacitor gets, the harder it is to charge further. Just like blowing up a balloon, the first breath is easy, the last breath is hard. The air in the balloon builds up its own pressure. The total energy stored in the balloon is not the final pressure times the total air. We didn't do gases in this class. I don't know if you did that. Anyone do that in your chemistry class? Probably not. No? Yes? Maybe? Okay. So the moral of the story, what I'm giving at here, I'd like you to focus on the second equation first. If I look at a total amount of charge and a total amount of voltage, total amount of energy stored in the capacitor is half of that. These other forms can be obtained by Q equals CV and substituting what you don't want. If you plug in Q equals CV and get 1/2 CVV, that's this version. If I don't want the V, I can solve for V equals Q over C, Q over C, Q squared over C times half. It's not really 4 equations I'm giving. It's 2 equations. This Q equals CV, and this total energy stored is half QV. Stored. Once upon a time, I wrote down the equation. Deja vu. Total change in position you can get by the formula with acceleration in it, or at first you can calculate the average velocity. The miles that you cover is the average miles per hour times the hours. If you have a way of finding the average velocity. Do you remember this? Is this making connections? Sort of? Okay, so on the emphasize. If you go from 0 miles per hour to 10 miles per hour, what's your average? 0 to 10 on average is 5, right? Add the two numbers, divide by 2. Deja vu. The other form of this formula, I occasionally wrote 1/2 V final plus V initial times T. Deja vu, or I think I usually wrote this as a fraction. That look familiar? So this is the average, and this is T. What happens if I start from 0? It's just half of your final velocity times time. That's where this comes from. The average voltage that the charge on the capacitor plates feels is half of the final. Just like the average velocity is half of the final max velocity. Turn to your neighbors. Tell each other the story of this half. I don't want you to confuse total energy is test charge times voltage with capacitor energy was half QV. 2 minutes, give me a question, and then you're free, okay?
It's doing this. Oh, that is so you could average it out. So we're assuming it's always zero. So if it's 0 plus something, we don't even do it.
I choose that.
Or if it's an average, we divide it by 2. So that's where the half goes. So rather than saying 0 plus final over 2, we're just gonna say final over 2. We don't need to add anything.
The director of the
Well, anything, you're right, anything plus 0 is itself, not both. But where did that voltage come from?
All right, we got like 1 minute left. Give me a question, we're free. Yeah. Yes. Well said, brava. You're free. Get out of here. I love you all. Bye.